Hello there, this is Ms. Page, and in this lesson we are going to talk about the remainder theorem. And in math, the remainder theorem is something that we can use to help us determine the zeros of a function when our factoring skills won't initially help us. And so it will use one of our skills of long division of polynomials, which we see here, all right, as a refresher when we divide polynomials. In our problems today, this would be what our function would be equal to, and this would be one known factor of the function, which we can be given directly or we can get if we know one of the zeros of the function. So here is the remainder theorem written out mathematically. So we're looking at if we know that r, which is a number, is a zero of a polynomial function here called f of x, then x minus r is a factor of that function. We've done that before. Like if we know that we have a zero that's equal to 2, then we know that's a value of x, and we can work backwards towards getting the factor of the function that zero came from. In this case, x minus 2 over here in my little example. That's what this is talking about. And so we can be given the factor directly, or if we're be given the zero, we can find the factor. And then we're going to take that factor and divide it into our function. If our remainder is 0, then we know that the quotient here called p of x is also a factor of the function, and that if we can factor it, then we can find other zeros of the function. So that's what this is talking about, the procedure here for using our remainder theorem. If we have a given factor, or we're given a zero and we create the factor that it came from, we're going to use our division skills to divide the function by the given factor of the function, or the factor that we have of the function. Then we will write the function as a product of its factors. That would be our quotient that we get from step 1 and the factor that we divided by. That's what this is talking about here. Not to forget that the factor we were given is part of the factorization of the function as a whole. Then we would factor further if necessary, and most of the times it will be. And then once we have a product of factors, we can use our zero product property to then continue solving for the remaining zeros of the function. All right, so in this particular problem, we are given a factor of a polynomial function, and that's what this is right here. So x plus 5 is a factor of this function here, f of x, which is a cubic function. We are to find all of the rational zeros of the function and include any multiplicity. So again, if a zero repeats itself, then we'd write that zero more than once to show its multiplicity. Notice it says rational zeros. Remember, rational numbers are numbers that can be written as ratios or fractions. So here we're not looking at irrational zeros or imaginary zeros. We're just looking at rational zeros. And then we will sketch the graph of the function to bring in some prior skills too. We've done that before. All right, so the first thing we're going to do is use our long division skill. So we're going to take our factor of x plus 5 and divide it into our function here. Remember that when you're doing long division, to look for missing terms in your dividend, which is our function here. We don't have an x squared term, so I'm going to put a plus 0x squared in that spot, because I will very likely have x squared terms as I go through this. So then we take our x, and in the division step we figure out what times x equals this x cubed term that we have at the front, which is x squared. So I'm going to put that there. Then we will distribute the x squared, multiply it times the x plus 5, which gives us x cubed plus 5x squared. And then remember, critical here, that we understand we are subtracting that quantity. So before we combine any like terms, subtraction is adding the opposite. So we need to change the signs on our x cubed and our 5x squared before combining. So this becomes plus a negative x cubed and a negative 5x squared. And then these would become 0, which they are, this first pair is always supposed to add up to 0. And then 0 plus negative 5 will give us a negative 5x squared. Bring down our minus 19x. And then we go through the process again. So here we're looking at what times x equals negative 5x squared, which would be a negative 5x. So we have minus 5x. We distribute that, which gives us negative 5x squared minus 25x. Again, we have to realize that we are subtracting that quantity. So we need to change the signs before combining. So this becomes plus positive 5x squared, positive 25x. And then combining, negative 5 plus 5 is 0. Negative 19 plus positive 25 is positive 6. So we get 6x. Bring down our plus 30. And one more division. What times x equals 6x would be a positive 6. That gives us 6x plus 30. Now here's the thing about these problems that's different from just a regular division problem. At this step, you should expect to get a remainder of 0. If you get a remainder of something else, then you've done something wrong. Because remember, x plus 5 is a factor, which means that it should divide evenly into the function, giving it a remainder of 0. So here we get a negative 6, a negative 30, 6 and negative 6 is 0, 30 and negative 30 is 0. So that then tells me, okay, I'm good there. So now what I want to do is realize that my quotient here times my divisor equals my dividend. So my function f of x, which is x cubed minus 19x plus 30, can also be written as a product of my divisor of x plus 5 and my quotient of x squared minus 5x plus 6. So this is where we're to the point where we're going to factor this further so that we can get at the rest of the zeros. So to find our zeros, we know our function value would be 0. That's our y value. And this would be still x plus 5. And our trinomial here factors into the binomials of x minus 3 and x minus 2. The zero product property then says one of these factors has to be equal to 0 for our product to be equal to 0. So either x plus 5 is 0, x minus 3 is 0, or x minus 2 is 0. So our zeros here, we get negative 5, we get 3, and we get 2. So those are all rational numbers. They're also all integers. And so that gives us our answer to part A. We don't have any multiplicity this time, but we do know now that our zeros are from least to greatest, negative 5, 2, and 3. So now we can create our graph. So now we draw in our axes here. We have our zeros at negative 5. So again, we'll just use scales of 1. So this is negative 2, 3, 4, 5 would be right there. And then we have positive 2 and positive 3. The other thing that we need to, of course, be aware of is end behavior, which we've previously learned about also. So the first term of our function is positive 1x cubed, which means that our end behavior would be right end going to positive infinity. And with cubic, the left end then goes the opposite direction. So it's going to go here into the third quadrant. So our function then is looking like this. That's a sketch of this particular cubic function. All right, let's take a look at another problem. So here we have our function f of x, and the factor that we're given here is this x minus 2. So again, in order for us to find all of the rational zeros of this function, our factoring skills here may not work on this, so we would take and divide our x minus 2 factor into our function of negative x cubed plus 12x squared minus 45x plus 50. Whoops, need a 5 in there, don't I? And so this time we need to figure out what times x equals negative x cubed. It should be a negative x squared. And that would give us the negative x cubed plus 2x squared. We would subtract the quantity, so changing the signs, we get plus positive x cubed and negative 2x squared. Negative and positive x cubed add up to 0. 12 plus negative 2 gives us a positive 10x squared. Bring down the minus 45x. So x times 10x would give us our 10x squared, so we get plus 10x. And that gives us 10x squared minus 20x. Again, we are going to subtract that quantity, so we want to change those signs before combining. So this becomes plus negative 10 and positive 20. 10 and negative 10 is 0. Negative 45 plus positive 20 is negative 25. X, and then bring down the plus 50. And then x times negative 25 gives us that negative 25x and plus 50. So again, remember that if we've done our math right here, this last subtraction should give us a remainder of 0, which we get a plus positive 25, negative 50. Negative 25 and 25 is 0. 50 and negative 50 is 0. So there's our remainder. So now we are going to take and write our function. So the division's our first step. The second step, we're now going to write our function f of x as a product of its factors, which are the x minus 2 and our quotient here. So f of x equals the x minus 2 times the negative x squared plus 10x minus 25. And we're going to factor this quotient further and to finding our zeros. So our function y value is 0. Now with personally, and I've shared with you this strategy before, if my first term in standard form is a negative, I like to factor out a negative common factor, which would be a negative 1. So this would be times a negative 1. And then that would become a positive x squared minus 10x plus 25. And then this trinomial here becomes a little easier to factor that way. I can more easily see it's x minus 5 times x minus 5. So my zero product property here, it says that, now remember, negative 1 cannot be equal to 0 because it doesn't involve x, so we'll ignore that factor. But x minus 2 could be equal to 0, and of course x minus 5 could be equal to 0, or the other x minus 5 could be equal to 0, which gives me zeros of 2, 5, and another 5. So I've got that multiplicity here. So those are my zeros in the answer to part A. So for part A, my zeros are equal to 2, 5, and 5 again. All right, so now we are going to graph this. So our zeros are at 2 and at 5. And remember, we have that multiplicity at 5, so we don't want to forget that. And our end behavior is based on our first term of our function, which is a negative x cubed. So that means our right end is going to go down here to negative infinity, and our left end would have to go the opposite direction, so it's going to end up here. And I have that multiplicity, which means that as the function moves through, that will be a relative maximum because of the multiplicity. All right, let's take a look at a third example here. All right, so here on this one, we have our function, f of x, and here is our factor that we know for our function. So we're going to take our remainder theorem, or use the remainder theorem here, and divide our function by its factor. Let's see, we don't have any missing terms, so no zeros necessary. All right, so we begin this process. X times negative x cubed would be negative x to the fourth, and that would also give us a plus 3x cubed. We are going to subtract, remember, so changing those signs. It's going to give us plus a positive x to the fourth and a negative 3x cubed. These would be 0. Negative 2 plus negative 3 is negative 5. X cubed. Bring down the 16x squared. X times negative 5x squared is our negative 5x cubed. Distributing gives us also a plus 15x squared. Subtracting, we get plus positive 5 and negative 15. 5 and negative 5 is 0. 16 plus negative 15 is positive 1. So we get positive 1x squared. Bring down the 2x. Then x times x would give us a plus x. That's our x squared. We also distributing get a minus 3x. Subtracting. Changing the signs, we get plus a negative x squared and a positive 3x. X squared and negative x squared is 0. 2 plus 3 is 5. Bring down the minus 15. And x times 5 is our (5x), and distributing gives us a minus 15. So again, remember here we should have a remainder of 0, but we don't want to assume. We always want to double check it. So this is going to give us a plus and a negative 5 and a positive 15. 5 and negative 5 is 0. Negative 15 and 15 also is 0, so we get that remainder of 0. All right, so moving on to the next step. So we are now going to write our function now as a product of factors. Those factors would be after our division, our divisor, and our quotient. So our function now is our x minus 3 times our quotient of negative x cubed minus 5x squared plus x plus 5. So again here, I have that negative leading coefficient. So personally, when I go to complete my factoring, I would factor out a negative 1 before I do anything else. So this becomes x cubed plus 5x squared minus x minus 5. Makes everything else a little bit easier from here. So now what I want to do is recognize on this 4-term polynomial I want to use my factoring by grouping. So I have a GCF of x squared for the first 2 terms and a common factor of negative 1 for the last 2 terms. So this gives me x squared minus 1 times x plus 5 and x squared minus 1 is a difference of two squares, so I could factor it further, or I could use my square root property when I go to solve for my zeros. I'm just going to go ahead and factor it. So what I've got for my complete factorization is I have this negative 1, and then I've got this x minus 3, and I've got this, which becomes x plus 1 and x minus 1, and I've got the x plus 5. So again, when I go to find my zeros, negative 1 can't be equal to 0, so it's not going to give us a value of x. X minus 3 could be equal to 0. That will give us a 0 of 3. X plus 1 could be equal to 0. That will give us negative 1. X minus 1 gives us positive 1, and x plus 5 gives us negative 5. So we don't have any multiplicity this time. We do have 4 zeros, however. So that will be our answer to part A. So our zeros are equal to negative 5, negative 1, 1, and 3. And now for our graph. Sketch of our graph with the information that we can get at this point anyways. So no multiplicity, so we've got a 0 at negative 5, and at negative 1, and at positive 1, and at positive 3. So in behavior, we have a first term of negative x to the fourth. So that leading coefficient of negative 1 being negative tells us that our right end is going to go to negative infinity. Because it's a fourth power, a quartic, both ends have to go the same direction. So that means our left end also goes to negative infinity. And without any multiplicity, our function just moves through our zeros. Let me try that again. There we go. And there is our sketch, and that finishes it. So from here, we have some practice problems for you to give a try. So here's a practice problem for you to try. Pause the video here. All right, let's take a look at the result. So the long division is not shown here, but this work starts with writing our function as a product of factors and setting it equal to 0. So your quotient of your long division should have been negative x squared minus x plus 6. Then finishing your factoring gives us this, and then using our zero product property gives us the rational zeros of negative 3, 2, and 4, no multiplicity. Our first term is negative x cubed, which means our left end has to go to negative infinity. Or sorry, our right end has to go to negative infinity. And our left end has to go the opposite direction, which is up here at positive infinity. All right, let's try another one. Pause your video here. All right, let's take a look at the result. All right, so again, this picks up with after the long division. So this would have been the quotient in your long division. And this is, of course, the given factor. And we're setting it equal to 0 to find our zeros. So here we have to use our factoring by grouping strategy. We get an x squared GCF here and a negative 16 GCF there. And then the product. And x squared minus 16 is a difference of two squares. So again, you could use your you could factor it further, or you could use your square root property on that. Here it's factored further. And then we get these zeros, and 4 does show up twice, so that we do have some multiplicity. Here it's shown with the other notation, but you could just write 4, 4. That would be fine too. And your end behavior comes from your first term, x to the fourth. So it's a positive 1 leading coefficient, which means our right end goes to positive infinity. Being a quartic, fourth power, that means both ends have to go the same direction. So our left end also has to go to positive infinity. All right, got one more here for you to try. Oh, nope, it's a closure. Okay, so one of the things about this closure that I wanted to make clear to you guys, so this says, explain why the remainder theorem can't be used to find the zeros of this function using x plus 4 as a factor. So here, apparently, x plus 4 was a factor. Now, this division is all correct. So if we look at all of the math is done correctly. And what we end up with here is a negative 32 as the remainder. So that is telling us that this right here, x plus 4, is not a factor of this function, even though somebody thought it was. So that's another thing too. You have to be real sure that what you're dividing by is a factor of your function. Otherwise, you will not get a remainder of 0, and you can't then find your other zeros this way. So we have to make sure that we're using a correct factor here for our remainder to be a 0. So keep that in mind. All right, that ends this lesson, and have a great day.